Good afternoon, everybody. Welcome to today's lecture, Ancient Light, the Microwave Background Radiation and Cosmology. Let me give a very brief introduction of our activities to our distinguished guests and all the audience. Jawaharlal Nehru Planetarium is engaged in dissemination of science through various programs. We have popularization programs aimed towards general public, namely Sky Theatre programs attracting over 250,000 visitors every year. Then we have sky watching programs, screening of science movies, etc. These attract thousands of people every year. We have in-depth non-formal science education program, starting from school students up to undergraduate students. These students attend classes throughout the year. Our non-formal programs have produced over 110 students who have pursued PhD programs and are now involved in research or in teaching. We organize public talks in association with research institutes. We have had over 12 talks in last 1 year in association with ICTS. And just last week, in association with IIA, we had a talk by Professor Patrick Michael, Director CNRS France. And today, we have this talk in association with British Council. We have associated with British Council earlier also. We had a talk by Professor Robert Stone long back in the program Bright Sparks. Again in the year 2004, we had an exhibition of astrophotos by Dr. David Malin. And in 2009, we had an exhibition titled Darwin Now. And with this talk, we are continuing our association. Today, we have this lecture by eminent scientist, Professor Mark Birkinshaw. I thank British Council for coordinating and making this happen. Professor Birkinshaw is a very distinguished scientist. He is William P. Coldrick Professor of Cosmology and Astrophysics in the University of Bristol. He has very rich experience. He has worked in Mullard Radio Astronomy Observatory of Cavendish Laboratory, where he got his PhD in 1979. He worked as a research fellow at Gonville and Case College. He then joined Harvard University as professor of astronomy and then joined Smithsonian Institution, where he worked on Chandra Observatory of NASA. He is an expert on structures in microwave background radiation created by clusters of galaxies, on relativistic effects that distort the appearance of distant objects, and on the interactions between outflows from active galaxies and the diffuse gas around. He has published more than 400 papers. I extend a very warm welcome to you, sir. I extend warm welcome to all the guests and the media who have been helping us in reaching out to larger audience. Now I request Professor Birkinshaw to deliver the lecture.
Thank you all in advance for coming. I hope I don't torture you too much. What I'm going to do over the next hour is introduce, firstly, the microwave background radiation to you and show you why it is such an important quantity in cosmology. And then I'll introduce 3 satellite projects since the late 1970s that have told us progressively more about the properties of the microwave background radiation and informed us about, in some ways, how complicated our universe is, but in others, how simple it is, in that the structure of the universe can be described by a physical theory that relies on just 6 parameters, just 6 numbers which are relevant. And I'll explain what at least some of them are. So, I'll start with some history. And the 3 satellites I'll talk about are COBE, the Cosmic Background Explorer, Wmap, the Wilkinson microwave anisotropy probe, and Planck, which is just Planck, named for the person who first described the thermal spectrum of radiation that comes from dense and hot matter. So to go back to the beginning, these two people are Arno Penzias and Bob Wilson. Bob Wilson is on the left in the rear because he was the junior partner in the enterprise. These people were employed by Bell Laboratories in the 1960s, and their work was to try to understand why radio communications across the United States weren't as good as they were expected to be. That is, when you send a radio signal from one side of the United States to the other, there was more noise on the communication than they wanted. They used the large horn that you can see behind their heads as a telescope to point around the sky to see if they could find the source of that noise. The first source of noise they found had to be dug out of the telescope with a spade because it was pigeon droppings. Birds had managed to nest in there. Having cleared what in their paper they call white dielectric material from the telescope, they were able to use it to make rather precise measurements of the brightness of the sky. They discovered that the sky has radiation in it from the galaxy, and that is distributed like the galactic plane. That's not a problem to understand. But there was a persistent excess brightness corresponding to about 3 Kelvin, which was distributed uniformly over. This is an excess noise that they said had a cosmic origin, and that we now call the cosmic microwave background radiation. It provides, if you like, the backdrop to the universe. It is the universal radiation field that comes from very early in the universe and propagates to us today. It tells us more than anything else about the very early universe, but it also tells us about everything that it washes past as it comes towards us. Now, the idea that there had been a background radiation had been around since the 1940s. On the left there, George Gamow, and in the middle, Ralph Alpher, had worked together trying to study how heavy elements are formed in the universe. Much of the material in the universe that we know about is hydrogen, helium, lithium, beryllium, boron. But theories of how those elements can be formed in stars didn't work, not properly. There had to be another source of nucleosynthesis, the making of the heavy elements. And they decided that the origin of those heavy elements was in an early dense phase of the universe, shortly after the Big Bang. Amusingly, the paper that they wrote on this is known in astrophysics as the alpha beta gamma paper, because it was written by Ralph Alpher, Hans Bethe, and George Gamow. Hans Bethe, I should say, actually did no work on the paper, and his name was added by George Gamow as a joke. I think he only found out about the paper after it had been submitted. After doing that work, which predicted that the brightness of the background radiation would correspond to a 40 Kelvin temperature, Ralph Alpher moved to George Washington University, and with Bob Herman, who's the forgotten member of this team in many of the historical discussions, worked with Ralph Alpher to come up with an improved prediction. And the improved prediction was that the brightness of the background radiation would correspond to a temperature of 4 Kelvin. Now, the difference between 40 Kelvin and 4 Kelvin is only a factor of 10, but because of the way thermal radiation works, that's a factor of 10,000 in intensity. And where a 40 Kelvin radiation could have been detected in the 1940s, a 4K one couldn't. So this result just sort of languished in the literature for years until Bob Dicke, working at Princeton on the left there, decided that his recent invention of some new radio astronomy equipment made it now possible to go out and look for the radiation field. So he and his students in 1965 were building a piece of equipment to go and look for the cosmic microwave background radiation to follow up this earlier prediction. One of his students in the middle there, David Wilkinson, is the person for whom the Wilkinson microwave anisotropy probe was named. Before they were able to complete their equipment, they had a phone call from Bell Labs, from Penzias and Wilson, saying that they'd found this extra noise and did they have any idea what it might be. And rather famously, Bob Dicke put the phone down, turned to the students and said, "Sorry folks, we've been scooped." As a result, Dicke and his students did not get the Nobel Prize for discovering the background radiation. They missed by a few months, whereas Penzias and Wilson, who were trying to do something completely different, did get the Nobel Prize. Now, this idea that a hot universe started off and created the elements that we now know and love, and that it possessed a radiation field, is based on the work of this individual, Alexander Friedmann, who was working at the Perm University in the 1920s, shortly after Einstein published the general theory of relativity, the theory of gravitation that we now know is extremely precise. What he did was to realize that you could apply the relativistic equations to the entire universe and describe the expansion of the universe by a single function, a function we call the scale factor, which changes with time. And the graph on the right is based on Friedmann's equation and shows how the size of the universe changes with time. Along the y-axis, I've put the scale of the universe relative to the current scale, and along the horizontal axis, the time in the universe since the Big Bang. When the universe is at t equals 0, 0 time, everything was concentrated down to a point. The scale is 0, so that all points in the universe were at a single point. As time goes forward, the universe expands, and the matter in the universe, through the effects of gravity, causes the expansion to slow down. And you can see the curve curves down a little bit. But then a strange thing happens. And after about 3/4 of the current age of the universe, the curve starts to go up again. The universe is accelerating away. That accelerated expansion is the result of the action of the second gravitational constant. The constant we now call the cosmological parameter lambda, which is driving an accelerated expansion of the universe, causing things to move away from us faster and faster. Now, if the universe started small, and we now know its temperature, we can run the clock back and say if it's this temperature today, when it was a little bit smaller, it would have been hotter, and it would have been even hotter in the past, and extremely hot when the universe was very compact. That's essentially the idea that George Gamow and Ralph Alpha were using. But that means that all the ordinary matter like hydrogen and helium, when it got hot enough, would have been ionized. And the neutral matter we have today would have been broken into nuclei and electrons. When the nuclei and electrons are all buzzing around, they interact very strongly with matter, with radiation, and they can produce radiation. They produce light. And it is light. The sort of frequency at which the radiation comes out corresponds to the sort of light that you see from the surface of the sun, because it's exactly the same process. And in a sense, the universe we're in is in the center of a giant sun, which happens to be 13.5 billion years away from us, so we don't get fried. As the universe expands, the radiation expands with it. So what was radiated as something like starlight gets shifted from being in down into the infrared, and then below the infrared into the submillimeter, and today it peaks in the millimeter wave band. And it goes from a temperature of about 3,000 degrees to a temperature of about 3 degrees when the universe expands by a factor of 1,000. So the universe is now 1,000 times larger than it was when the microwave background radiation was released. And since the universe has been neutral since that release to the present, the radiation that was released comes to us without seeing any more electrons and ions flying around with which it can interact strongly. It doesn't pick up their temperatures, and we get a nice clear picture of that early phase of the universe, 13.6 billion years ago. When I say it doesn't interact, it doesn't quite interact. There are some small subtleties. Now, before I go on, I should just introduce redshift. I'm going to use the word redshift frequently. Now, I've already used this technical word, the scale factor. Redshift and the scale factor are saying the same thing in different language. Redshift 0 is what we mean by today. And that corresponds to when the universe is the same size as it is today. Fairly obviously. And the equation that we use is to write that the redshift plus 1 is equal to the ratio between the size of the universe today and the size of the universe at some other time. So if the universe was smaller in the past, that ratio is greater than 1, and the redshift is greater than 0. In the future, where the universe has expanded, that ratio is less than 1, and the redshift becomes negative. So negative redshifts correspond to the future, positive redshifts correspond to the past, and the function that describes how time relates to redshift is plotted there on the right. Almost all the galaxies and quasars and other things we know about in the universe lie out to redshift less than 4. And if you look at the curve there, that says that that is looking back to about 11.5 billion years before the present. If you look at how the curve flattens, that's because the age of the universe is only about 13.7 billion years, and that corresponds to redshift infinity. 13.6 billion years corresponds to redshift 1,000. So the difference between 1,000 and infinity is only 100,000 years, but is infinity in redshift terms. Okay, so I've given you a picture about where the microwave background radiation comes from, but at the moment it's a fairy story. And it's a fairy story because it's not tested in any scientific way. And if we want to test our ideas, we've got to go out and prove that what we've said isn't wrong, or maybe find something else that tells us a better way of explaining what we're seeing. So the first thing you might ask is, well, we see this uniform radiation field. How do we know it doesn't come from just outside the solar system? Well, one good way of doing that would be to see whether in the passage of the radiation coming towards us, there are objects out there that cast shadows. And if you know the distance of those objects that are casting shadows, you can say the radiation comes from behind that. So let's try to find some shadows and prove that the radiation is away. The second thing you can do is say, well, we also know that the theory tells us that the universe was dense and produced this very special blackbody radiation at a single temperature that was emitted towards us and has now spread out from short wavelengths to longer wavelengths, gone from the optical to the radio. So it should still look like a thermal spectrum here today. So can we prove that the radiation field is thermal? And finally, when they were looking at the microwave background radiation, they saw it was uniformly distributed over the sky. Is it really uniformly distributed over the sky? If it's not, maybe that helps us by finding out something else about how the universe works. Now, the first one was the easy one, but it must have been because I was able to do it. And what we did was we took a telescope and we measured in the directions of objects that we thought would be casting faint shadows on the background radiation. Those objects are clusters of galaxies, which are roughly 3 million light years across, and contain enough matter which has been reheated that they look like the sort of denser material that the radiation field will interact with. And in the directions of the centers of each of those 3 clusters, you can see the graph shows the central point is quite low. That's a faint shadow. I say it's a faint shadow because the drop in the brightness is 1 part in 3,000. So it's an extremely faint shadow compared with the sorts of shadows that buildings cast in the daytime, for example. Now, the other questions are rather harder to answer. And for that, we had to go into space. And the first of the space satellites was the COBE satellite, the Cosmic Background Explorer. You can see an artist's impression of it on the left. It was a relatively ugly thing. And it contained 3 instruments set within that gold-colored radiation shield on top of the spacecraft. On the sides, the paddles are solar panels that pick up energy from the sun and have enough, provide enough electricity to keep the thing running. That radiation shield. 2 main instruments of interest to our story are the DMR, which is that gold-covered box in the middle, and the FIRAS, which is the black cylinder on the right-hand side. The black cylindrical thing is shaped, in fact, like a trombone horn, and it exists to take in radiation and concentrate it at the end and take its spectrum precisely. The device in the middle, tiny little horns, which point in different directions, and the instrument measures the difference in brightness that comes in from those 2 different directions, and then sends that down to the ground. And if the sky is lumpy in the microwave background radiation, then in some parts of the sky you'll see a signal. If it's not lumpy, then you won't. And as the spacecraft rotates around the Earth and tumbles, it gradually makes up a picture of the entire sky. Now, the spectrometer device has a little dunce's cap that sits on top to calibrate it. They were so worried about how this would work in orbit that as soon as the satellite was in orbit, they made a measurement with that instrument in case it jammed later. And if it jammed with a hat on top, you wouldn't be able to see out. And this is the picture they got. This is based on 15 minutes of data taking with the satellite. What you can see there is a curve, which is the Blackbody radiation curve that's theoretically there for a temperature of 2.73 Kelvin. And the white spots which you can't see are the data points. And you can't see them because they perfectly follow the curve. In other words, in 15 minutes, this satellite that took 15 years to build was able to prove that the radiation is thermal and very nicely matches a 2.73 Kelvin black body. Well, that's in fact a fake curve, because the far infrared, the spectrometer, actually measured the difference in temperature between the sky and an internal calibrator. And what the NASA publicity people have done is add back in the curve for that calibrator, so you can't really see the details. But believe me, it's still a perfectly acceptable, beautiful thermal black body. So now we know the radiation of the spectrum of the sky away from the galaxy is a beautiful black body, thermal radiation. How about the angular structure? The angular structure looks like that. And that is a color scale on brightness, and it shows that the color scale, thank you, the color scale corresponds to a uniform brightness of about 2.7 Kelvin over the entire sky, and there's very little structure. I hate to tell you this, but that also is a fake. And the reason that's a fake is that the instrument that measured it, I told you, only measured the difference in brightness in two different directions. And those kind people at NASA have added back in a uniform signal just to show that they've added back in a uniform signal. What the telescope actually measured was this. Now, that shows structure. Very clearly it shows structure. It shows, the Chinese characters spell yin-yang, by the way. It shows a yin-yang structure over the sky. But the brightness of that structure is only 3 millikelvin, whereas the brightness of the background radiation is 3 Kelvin, approximately. So this is a 1/1000th change in the brightness over the sky. So to very high accuracy, the sky is uniform. But it's not quite. If we look at that yin-yang structure, what causes it? Well, what causes it is the motion of the observer through the universe. When you are outdoors and trying to avoid the traffic, you know that a car that's coming towards you and sounding its horn has a slightly higher tone than a car that's receding from you and making another triumphant horn sound for having escaped. That Doppler shift of frequency that occurs with sound waves also applies to light and other radiation fields. And what's happening is that the Earth and the galaxy are moving towards the upper right of that diagram, so the radiation is slightly brighter and at a slightly different frequency up there. The amount of motion that's required is about 400 kilometers per second. But our sun is rotating in the galaxy at a couple of hundred kilometers per second, and when you combine the velocities correctly, it's about a 600 kilometer per second motion of our galaxy through the universe. So our galaxy isn't exactly standing still relative to this background radiation. And all galaxies jiggle around to some extent. It was a bit of a surprise that our galaxy was jiggling that much. Okay, so if we understand that, that yin-yang, let's subtract off that pattern and see what's left. You can already see there's a few lumps along the center line. Well, this is what's left. Okay, what's going on here? Well, the center line is the plane of our galaxy. So what you're seeing is that our galaxy is a bright radio emitter. And that radio radiation comes from exploding stars, the black hole at the galactic center, hot gas, maybe the mobile phones of Fred Nurk on a distant planet. But everything just accumulates and is general rubbish. So forget that red stripe and think about what's above and below it. And above and below it, you can see a sort of a patchy structure. If you look at the number in the bottom right-hand corner, that now says about 20 microkelvin. So this is now 1% of the brightness of the Doppler pattern. And that is where the cosmology is. That's the signal of some small lumpiness on the sky. We can only see it above and below the galactic plane. That lumpiness is telling us something about the lumpiness of the universe way back 13.5 billion years ago, just 100 million years after the Big Bang. Well, it almost is, and it almost isn't, because most of what your eye sees on this picture is measurement noise, because this was a small satellite. It only lasted 2 and a bit years, and it was using old-style technology. Nevertheless, a statistical analysis shows that there is real signal there. It's not just pure noise. Trust me on this. We'll see better in a minute. Okay, why should we think that there might be lumpiness in the early universe? The reason is that I'm not floating through empty space. we know that the universe contains significant structure, and that structure in the form of galaxies and clusters of galaxies and things like that, condensed by a gravitational collapse in some way. And this movie, what it shows is that if you start with an entirely uniform early universe, you don't get, by today, the sort of structured galaxies and clusters that we actually see. You have to have some lumpiness early on. If you have early lumpiness, then you take matter and you compress it a bit. When you compress it a bit, just like our previous story, it gets warmer. So the microwave background radiation gets a bit more intense. So a lumpiness in the microwave background radiation on scales which correspond to the formation of galaxies and clusters today has got to be there. And that's what this patterning above and below the plane is supposed to be. Now, I've got to show you a complicated graph, and I'll apologise for this in advance, but this complicated graph is going to tell us all about the cosmological parameters that define the universe. And what the graph is of the statistical properties of those lumps above and below the galactic plane. Hold on to your hat. Right, here it is. What this tells us is that the lumpiness signal is quite small at small numbers of this thing called the multipole. It then increases, and then it sort of bounces around a bit, then it drops down again. Now, multipole is our highfalutin way of talking about angular structure on the sky. A multipole of 2 corresponds to a 90-degree scale structure on the sky. Multipole of 100 is a 1.8 degree structure on the sky. Take 180 degrees, divide by L, that tells you the angular scale. It would have been much simpler to just set angular scale and plot it another way up, but whatever. Now, Kobe could only observe over that green range there. And the green range that I've highlighted is basically pretty unstructured. It just drops a little bit. All of the really interesting information is in the bouncy peaks and valleys on the right-hand side. They lie at high multipole and therefore small angular scale. So we should go off and take a look and see if we can see those higher multipoles. And the way it works is the angular scale that you can see depends on the size of the instrument you can fly. Kobe used an instrument that was about that big, 2 of them. Wmap used an instrument that was about 1 meter across, and Planck used an instrument that was about 1.5 meters across. In the case of both Wmap and Planck, they were real telescopes. They had a reflector and something looking at the reflector. Kobe was just the things that look out without the telescope, so it didn't have the advantage of focusing the light. And the images underneath the images of the satellites show you what the same bit of sky would look like when observed with Kobe, with Wmap, and with Planck. You see better and better precision of scale as you go to the larger instruments. And by going to the larger instruments, we can start to ascend the first of those peaks and the second of those peaks and see if that curve, which looks so complicated, actually makes any sense at all. So let's talk about Wmap. Wmap had this real radio telescope, so could make a proper image. It was stuck out a lot further from the Earth than Kobe was. Kobe was launched into a near-Earth orbit, which takes about 90 minutes to go around the Earth, like some of the recent Indian communication satellites. Wmap was launched way out to the L2 point. That is a point where it sits the opposite side of the Earth from the Sun, and gravity causes it just to move around at the same speed as the Earth goes round the Sun. So the Earth and the Sun always lie in the same direction. The advantage of that is that the radio signal from the sun and the radio signal from Indian radio and Soviet transmissions and the Chinese spy satellites are all behind the satellite in one direction and can be masked out. And Wmap images the sky to make the same sort of image as COBE does. If you take a look at the top left image, that roughly looks like the COBE image and is a low frequency map of the sky. It also observed in 4 other wave bands, and the left-hand set of images is what it saw. On the right-hand side, those are those same images from which a model of what the galaxy does to you is subtracted. So it's supposed to correct for the galaxy and show you the sky uncontaminated. You can see that there's still a red stripe towards the middle. In other words, we can't understand the galaxy well enough to subtract it properly. We can combine all 5 of those images, though, to try to minimize the effect of the galaxy. And when you do that, you get this rather spectacular picture of the cosmological sky as it would be if the galaxy was absent. Now, Wmap operated for 9 years. And 9 years was long enough that the noise, the random measurement noise on the measurements, drops below the signal strength in the microwave background radiation fluctuations. So where in the COBE picture I told you were seeing mostly noise, here what you're seeing is mostly reality. And I think your eye can see that this isn't just a random scattering of points over the sky. I see big continents and oceans with substructure in those continents and substructure in the oceans. Now that sort of structure is exactly what that complicated curve is supposed to show us. So let's see how that sky corresponds with the curve. Bingo. They match beautifully. Now, to make that match work, we had to diddle around with the dials that control the theory that tells you how much of different things there is in the universe and how much fluctuation there was very early on. And there are 6 important parameters and 1 very unimportant parameter in the set of numbers that's measured. The first parameter at the top there, thing I've written as omega bh squared, is how much ordinary stuff there is in the universe. And it tells us that there's about 2% of the mass density of ordinary stuff in the universe that would be required to stop the universe expanding forever, and just stop it and slow it down. Now we know already that galaxies aren't just made of ordinary stuff. There has to be cold matter there as well to provide enough gravity to hold them together. We call it cold dark matter. And I can tell you that any one of you who ever detects 1 particle of cold dark matter, report it, because you'll win the Nobel Prize. Nobody has yet found cold dark matter. We don't know what it is. It's a theoretician's invention of something that could provide the gravity and not have interacted in such a way as to appear as something else. But that stuff, if you look at the numbers, has to be 5 times as abundant as ordinary stuff. So for every gram of ordinary stuff, there has to be 5 grams of this cold dark stuff. The third number tells you that, well, fine, but both those things are much less important than lambda. And lambda is this cosmological constant which is causing the acceleration of the universe. And the fact that those numbers are smaller than lambda tells you the universe is accelerating away at the moment. And incidentally, there's no way back. Once something starts accelerating away, unless lambda decides to take a holiday, it's accelerating. The other numbers are much less important, I won't go into them. But those 3 key parameters describe the type of universe we're in. Now, over on the right-hand side, you'll see that I've shaded an area and marked it cosmic variance. The problem is the universe just isn't big enough. We've only got one point that we're sitting at, looking out at the universe, and we see one sky. But we don't know for sure that we're in an average place in the universe. The Copernican principle says to do cosmology you have to assume you're nowhere very special, but we could be just averagely bad. And averagely bad means that our sky could lie anywhere within that grey fan of measurement possibilities. And it does lie mostly within that grey fan. But can you see one data point that lies outside the fan? Underneath. A generation of cosmologists has agonized over that data point because even Kobe found that things didn't quite work on that angular scale. We'll come back to that in a bit. Now, one other number that I pulled out in that fit is tau, and tau is this number. There was that starred comment on one of the earlier view graphs. I said that the universe becomes neutral and transparent to radiation. This says that it's not quite transparent because when the universe becomes neutral, it doesn't go neutral instantaneously. There's a sort of a fuzzy period. And that fuzzy period corresponds to a 9% blurring of the fine-scale structure. A little bit of that tau is also the faint shadows that I went out and measured in the 1980s. Okay, if you've done a fantastic experiment and got a wonderful result, you shouldn't believe it until you check it. And that means doing it again. Science is all about getting reproducible results from independent investigations. And the Planck satellite, built by the European Space Agency, where Wmap was built by the NASA, then the American Space Agency, makes that duplicate observation. But it does it slightly better because it was built slightly later, contains slightly improved technology, has a slightly larger telescope. It also costs slightly less because it was built in Europe rather than in the USA, and we're a notoriously stingy lot. So that's what Planck looks like. It's a telescope with a whole set of little horns which are looking up at it and then get reflected out to the sky. Planck looks in 9 bands. And there are the 9 bands pictures that Planck makes of the sky. I don't know about you, but I get slightly depressed when I see this because where in the Wmap image the galactic emission was constrained to a little band across the middle, here you can see that that band extends right the way up over the entire sky. That is, galactic emission is important everywhere, has to be corrected for everywhere. However, the measurements that Planck made were so precise, and the galaxy has an effect that's different to the thermal spectrum of the background radiation, you can calculate a correction function. And when you do that and average all the bands together, you get this microwave background map of the sky that's currently the best available. Well, when I say it's the best available, it's not. And the reason it's not is because that projector isn't good enough. And my laptop isn't good enough to hold the picture. Planck measured the sky with unbelievable resolution so that there are many more pixels on the sky than we can project with that projector. And it's being degraded here with the result that that picture looks almost identical to the Wmap picture. You can see the continents and oceans in exactly the same place. And you can see the mountain ranges and peaks and other things on them in exactly the same place. We're measuring the same structure. The sky really does look like that. And if you calculate that complicated curve, the lumpy curve, from the Planck data, you see pretty much what Wmap saw, except you see it out a lot further. You see it out a lot further because that corresponds to higher multipole, which is smaller angular scale because you've got a bigger telescope. And that's the way Planck was designed. You also see, by the way, the far left-hand point still lies well below the line. The worry continues. Well, you can fit the cosmic parameters with that curve just as well as you can with the Wmap curve. And then we should compare our results and see whether they match. And so there's a giant table of results in the literature. And the right-hand column basically tells you everything matches to within normal statistical expectations. Wmap and Planck confirm the picture of what there is in the universe, how much baryonic material there is, how much cold dark material there is, how much cosmological constant there is accelerating the universe away. So we now have a wonderful working model, well, apparently working model of what the universe looks like. Now, because Planck is a big telescope, or bigger telescope, you can look at some of the features that the microwave background radiation washes past as it comes towards us. So let's go back to those shadows that I measured all those years ago. And Planck also sees those shadows. And this is a shadow associated with a set of clusters of galaxies in the southern sky, which lie close to one another and produce a nice footprint-shaped hole in the microwave background radiation. Okay, so we've flown a satellite. We've spent, well, in total about $15 billion worth of taxpayers' money. So we'd better admit whether we've got anything useful out and tell people what it was. And the first bit of useful knowledge is that everything fits a hot Big Bang cosmology. That is, the universe started hot and has expanded since then, releasing this radiation field that comes towards us. The second fact from the beautiful match of the data points to that lumpy curve is that structure in the universe, galaxies and clusters of galaxies, formed by the activity of gravity taking the little early fluctuations and amplifying them and compressing them down to make galaxies and clusters. The third fact, there are 6 numbers that have been measured with reasonable precision that tell you how the universe works. And if you put those 6 numbers into your computer, you will get a nice picture of what the universe looks like today, whether you're in China, India, Britain, the USA, or somewhere on the surface of the moon. Here's an interesting one. We also find that space-time is flat. Now, general relativity allows space-time to be flat or curved. And you know that general relativity says that near the sun, space-time is curved, and it's that curvature that holds stuff in. That's the modern way we understand gravity. On the large scale, the same thing could be true. What's the sum of the interior angles of a triangle when you draw it on a piece of paper? 180 degrees. What's the sum of the interior angles of a triangle if you draw it on the surface of a sphere? More than 180 degrees. If you draw it on the surface of a saddle, less than 180 degrees. That's zero curvature, a flat space-time. Positive curvature, you get extra angle. Negative curvature, you lose out. Our universe has chosen the most boring possible sort of geometry where Euclid's postulates work beautifully. Now, is that a coincidence? And the answer has got to be no, there's got to be something that does that. And that thing that does it is what we call inflation, which is a theory about the very early universe and tells you that there is a process which will force the universe that we see to be flat for almost all observers in almost all possible universes. Another fact that comes out, and I didn't emphasize this, there's only 3 types of neutrino. electron neutrinos, muon neutrinos, tau neutrinos. And those particle physicists are looking for a fourth neutrino and a corresponding fourth quark can forget it. If there was a fourth neutrino present, the heights of those bumps wouldn't be in the right ratio. I should say, by the way, that building a really top-flight particle collider costs more than these experiments, so we're cheap. Another result, because we can see the universe is dominated by this lambda quantity, it's dominated by what we call cosmological constant. And that cosmological constant has to be constant. It doesn't have a way of changing. And in some theories, the cosmological constant is itself a field of some kind, something like an electromagnetic field. Call it a electrogravitic field or something like that, that has its own ways of changing. But nothing in the measurements we've got here suggests that that parameter changes. In other words, general relativity rules supreme and you don't need to worry about complicating it. I just put about 500 theoretical physicists out of business. A few other things. You can see light from the microwave background radiation falling into clusters of galaxies, then coming back out again. But light can only travel at the speed of light. And a cluster of galaxies is 3 million light years across, so it takes light 3 million years to cross it. Over 3 million years, clusters of galaxies contract a little bit. And that means that the light goes in to a gravitational potential and drops down, then has to clamber out at a steeper gravitational potential to get out. That means that the light that goes in, as it drops in, it gets blue shifted. As it clambers out, it gets more red shifted than when it drops in. And we can measure that and see that happening in the directions of clusters of galaxies on the sky in the Planck data set. So we can see that clusters are still settling down today, and that's what the theory of gravitational information tells us. This idea about inflation that I said was present in the flatness of the universe is supported by one of those other parameters I didn't talk about, this thing called NS, the so-called scalar index. But not everything looks wonderful. I've said that that curve is beautiful and it reproduces beautifully the theory of structure formation, but it also tells you how many clusters there should be in the universe. When we go and look, we don't see quite that number of clusters, and they aren't distributed quite the way the theory says. So something is going on that's outside what the theory is currently telling us. Now that's great. I love disagreements between theory and experiment because it means that there's something we can discover. And the search for what might be responsible for that difference is a very active current topic of astronomical research. Either using ground-based optical telescopes to see if there are hidden clusters, or radio telescopes, or people thinking about more satellite projects. Another issue is the one I pointed out. That point at L equals 4, the point that lay below the curve is still below the curve, and in general the pattern of points in that part of the curve doesn't quite match up. Well, what's going on there? I don't know. One possibility is that when we had the Big Bang, the material didn't expand in a perfectly spherical expansion, but expanded slightly faster in one direction than another. And that will give you that type of distortion of the microwave background radiation. Another possibility, which is rather weird, is that in that direction across the universe, you come back and see yourself from the back, whereas in the other direction you don't. So in one direction the universe is closed, and in the other direction it's not. And that sort of topological structure, which looks like an American donut, is a possibility in general relativity, but nobody much believes it. Another issue on a much smaller angular scale is the so-called cold spot. We know how noisy the sky has to be because of all those lumps in that curvy line. And that tells us whether any particular location on the sky has got a probability of being as bright as plus 20 microkelvin or as negative as minus 20 microkelvin relative to the average. But there's one part of the sky which is much too cold. Now, a cold bit of the sky can be created by putting lots of gas there and making a bit of a shadow. Well, actually an anti-shadow, because the shadow actually makes the radiation hot. So you just have to take gas away on average. Now, people have gone to look to see if that is possible, and so far isn't. So there's this one direction on the sky that looks to be highly anomalous. It actually lines up with the thing called the axis of evil, which is a coincidence between the dipole term, the quadrupole term, and the octupole term, which all align in an unfortunate fashion. The probability of that alignment is actually not too tiny, and we could be that unlucky, but you can't keep appealing to luck. Something that I'd quite like to see in the Planck data and can't is this effect. It's called the Birkinshaw gull effect, and it arises because if you take a cluster of galaxies and move it across the sky, then like deflecting a cricket ball with a bat, you can give it a bit of extra energy or you can take a bit of energy away. If you give light energy, it gets brighter. If you take it away, it gets fainter. So the butterfly appearance at the top there on the left is from a cluster that's moving across the line of sight and is batting photons up to higher energy on one side and sucking them down to lower energy on the other. If we could measure this effect, we can measure how fast clusters are moving. If you can measure how fast clusters are moving, you find out more about how structure is forming than you do if you just know that there's a cluster somewhere. So it's a valuable effect to go after. Which brings me on to the next projects. People are still looking at the microwave background radiation because it is the thing that tells us the most about cosmology, about the early universe, that we can detect today. Most other things about the early universe exist only as equations or manipulations in computers. Now, when the next experiments happen, it's quite likely they will measure numbers that are consistent with our prevailing model of cosmology and do that more precisely. But every advance in physics in the last 150 years has happened when people have gone out and measured things more precisely and found anomalies. That's how quantum physics came about after all. And look how much use we make of quantum physics today. Most of you have got mobile phones in your hands or pockets. If that's true, and we find numbers that are drifting away from the error bands we get at the moment, we may find out something else about how the universe works, what the cosmological parameters are, and that would be intensely interesting. Now, another thing you can go out and try to do is measure the polarization of the radiation. I've only talked about its intensity, how bright it is, but Polaroid sunglasses work by saying there's less light in one direction than another direction. And just in the same way, if there are elongations of the universe early on in one direction than another, the light that we're getting from the microwave background radiation will be slightly polarized. And if the early universe had gravitational waves in it, along the same lines as the gravity waves that we've been detecting recently from colliding black holes and neutron stars, they will put an extra polarization signal into the microwave background radiation. Current information on polarization is poor. There are experiments on the ground that are trying to measure it, but to get polarization that's of cosmological significance, You have to measure it on large angular scales. You can only do that effectively from orbit. So there will be proposals to observe these things from orbit. Some have already been proposed, but the technology isn't quite there yet to make it work. But I know that NASA and the European Space Agency and the Indian Space Research Organisation are getting proposals to do this. And over the next decade, one of them is going to start building one of these satellites. And I'm sure there's another Nobel Prize lurking in that. And finally, just because of my early work, I think it's still interesting to go out and look for the properties of clusters of galaxies that are revealed against this sort of essentially white sheet of paper by the faint shadows they cast. And I would like to see really quite a large telescope in orbit or somewhere on the moon or somewhere good on the Earth that can make that sort of measurement sometime in the next 10 or 15 years. That's the future, and this lecture is now in the past. Thank you very much.
When the universe is expanding, the temperature is going down. So what happens when the temperature is approaching absolute zero? By what you said, it's around 4 Kelvin now. What are the possibilities that it actually approaches absolute zero?
Okay. That will happen in the infinite future, of course. And the idea is that matter then doesn't have any kinetic energy relative to the expansion of the universe as a whole. All it has is the quantum zero-point energy that causes what we used to call zeta-bewegung, the random motion of particles that are trying to be confined too closely. That will persist because the quantum properties of matter presumably aren't going to change. However, as you get to longer and longer times, it's possible that the particles we now know and love, like protons and electrons, will themselves decay away. Who said they last forever? We only know that protons last 13 billion years in the universe, and measurements of the proton lifetime have shown that it's only greater than 10 to the 32 years. So if you want to go a billion years in the future, maybe those particles will have vanished. Then what we'll be left with is just an energy field that sort of merges with this lambda field and just gives you a generic expansion of a rather boring grey universe, which is a sort of depressing picture. On the encouraging side, the universe in that accelerating state then looks a lot like the universe did at the Big Bang at 10 to the minus 35 seconds. So an interesting curiosity is, could that expanding, inflating universe then spontaneously regenerate a new universe just for fun? And that is the theory of chaotic inflation. That everywhere in an expanding universe you can just seed off a new baby universe somewhere that'll do its own thing. You'll lose all contact with it when you seed it off. A bit like one of your friends who moves overseas and then never sends a letter back. But that's probably what's going to happen.
My question was, how did you get that oval shape of the microwave background, and what does it imply?
Which shape?
The oval shape of it.
Okay, that oval shape I didn't explain properly. If you're trying to make a map of a spherical object like the sky, you can use a Mercator projection which just turns it into a cylinder like ordinary maps. Or you can say, well, that's not very good because it makes Antarctica look vast. We ought to do better. So that is just a way of mapping an entire sky onto an oval. You saw one of the early pictures I marked north and south, and there's the equator going around, and that central bit goes all the way around your head, around the back again, and you've got up and down, and when you fold it together you've got a map of the entire sky. So that's just a sky map expressed in an oval. But it's a thing called an Atov mapping, technically, which, look up if you want, but it's much better not to bother.
Hello, sir. I wanted to know if the epoch of reionization signal can be considered as a distortion in the CMB.
The EOR signal, let me explain what that is first. What I didn't say is that as the universe expands, matter and radiation cool at different rates. And the matter after recombination, after redshift 1000, after 13.6 billion years, is neutral. But we know that most of the matter in the universe today is actually ionized, so it's been reheated. When it was reheated, that was done by the very first self-gravitating objects that lit up and made the radiation, probably very early stars, POP3 stars, things like that. Since that process produced light principally in the ultraviolet and the optical, and that happened at redshift 10, it'll produce a radiation field that today is in the far submillimeter and the infrared, and hasn't redshifted down to confuse the microwave background radiation. If microwave radiation and the epoch of reionization signal will look like this. So they overlap once you get beyond there, but in the region where we're actually trying to do the microwave background measurements, they don't overlap very much. There's a slight distortion that we need to worry about, but it's probably not too much. But it is definitely something to worry about when you're getting very precise and getting up to the highest frequencies. This sketch, by the way, is a lousy sketch because this actually drops off very quickly, if I drew it properly.
So you spoke about the non-spherical expansion of the universe.
Yeah.
What's the idea behind it? What might have triggered? Because we know that the gravity acts equally all around. So what might be the possibility behind that theory?
Well, gravity acts equally, but who says you have to start with a spherically symmetric mass distribution? And it could be that that mass distribution started non-spherically. Let me illustrate that by a little experiment. Let's use the same stick of chalk. Okay, stick of chalk is standing up at the moment. If it becomes unstable, well, it's chosen to fall in that direction today. If I pushed it again, it might fall in some other direction because it's an instability. It's going to fall in some direction. If the Big Bang is an instability in some pre-existing state of matter, that instability could work in a way that causes it to want to expand a lot that way, or a lot that way, or a lot that way, or just sort of spherical. Now, when that field decays, it will leave the imprint of that original expansion choice somewhere on the radiation field. The imprint will be very faint because it will have been washed out by the rapid expansion of the early universe that we call inflation, but could still be present. So that's the thinking that goes into that, very approximately. Good question.
What are the questions of the microwave background raised that haven't been answered or yet to be answered?
Well, observationally, obviously the question will be the polarization. Now, and the polarization tells you more about the motions of matter at recombination than the intensity field does. So there's a lot of information about structure that's hidden in there. Another question is, it turns out that very early energy releases in the universe that happened before the universe went neutral will slightly distort the spectrum away from a pure thermal form to a slightly different form. It will take on a Bose-Einstein form, most likely, with a distortion parameter, which you measure by a thing called the chemical potential. that chemical potential could tell you about processes that happen in a part of the universe that's otherwise opaque. And it would be a really neat trick to start doing, essentially tunneling into the even earlier universe by using this chemical potential. And if that's true, and you can measure that chemical potential, then that bit of the universe and that bit could have quite different chemical potentials because of processes that were happening. And we could study something about how very early energy releases happen. So there's more to be learned in the spectrum as well. The spectrum is not as well known as it perhaps could be. So those would be the two things that I'd highlight. Plus, of course, my favourite, let's measure those shadows a bit better and try to get the motions of local objects. So the foregrounds contain a lot of physics that we're not currently making best use of.
In the inflationary model, basically the forces were all united in the beginning and then they split. So is there any proof in the cosmic background radiation about the time interval during when the forces split?
Basic answer is no. We can't say very much about the breaking of the symmetries in any grand unified theory of forces. The theory of inflation says that the rapid expansion of the early universe should happen before the electroweak transition. And the electroweak transition happens as long as 10 to the minus 26 after the Big Bang, which is ages. The inflation period is supposed to be a factor of 10 to the 8 closer to the Big Bang than that. Now, any transition between a unified strong, weak, and electromagnetic force that happens back there is good enough to do an inflation. The pure inflation people say, well, let's break the symmetry of everything and have it be a gravitational thing that does it. And then you're back at 10 to the minus 43 seconds, the Planck time. But as far as our observations of the microwave background tell us, all we need is an inflationary period, and we can't say which of those unifications is involved.
You said about the polarization data. If you get the polarization data, it will be more good for the cosmic background radiation. So if you remove that, the polarization data, will that cosmic background radiation will be more uniform or what? If you remove that data?
Well, the polarization signal is very weak. Under almost all models, it has to be rather tiny. So the fact that we don't take the polarization out properly from what we've got at the moment is probably not an issue. Because the polarization signal is sensitive to motions and anisotropies, the lumpiness, in a rather more strong way than the total intensity signal, theoretically we find out a lot more about lumpiness and motions induced by lumpiness in the period at around about recombination at about 13.6 billion years. So that's the main reason for doing the polarization. However, what I just said is mostly about one of the two polarization modes, the so-called E mode. There's another mode called the B mode, which is produced almost entirely by gravity waves in the very early universe. And going back to the earlier question, if it was a process involving grand unification of gravity and the other fields that caused the inflation, that would produce a lot of gravity waves early on, and they would leave a B-mode polarization imprint on the radiation field, even from as early as that, right through to reionization, recombination, and then reionization. So there's a lot of reason for trying to get a good polarization measurement, even though it's really, really tough. Polarization can be induced by all sorts of instrumental problems or telescope shapes and things like that. So it's a really difficult thing to get at precisely. But thanks.
Thank you. If space-time is flat, then shouldn't this background radiation also be like a band? Why do we see it everywhere?
No, the flatness is just a statement about what the interior angles of a triangle are. It's a geometry statement. It doesn't say the universe is two-dimensional. You can get flat three-dimensional objects. You can get flat seven-dimensional objects. And in string theory, you can get flat 13-dimensional objects, if you particularly want them. We're perfectly happy in doing relativity with a four-dimensional object, which is flat in the sense that if I take an object further and further away, its angular scale drops off like 1/, distance, exactly as you'd expect on a sheet of paper. And that's the technical meaning of it. In the physics meaning of it, that flatness parameter is one of the quantities that appears in the metric of space-time in general relativity. And its value, well, when it's non-zero, it makes all the general relativistic formulae to do with the universe horribly complicated. So it's a great relief that it's close to zero, so we can assume it to be zero when we fiddle with the equations, because it saves a heck of a lot of time and computer debugging.
We thank Dr. Mark Birkinshaw, descriptive, full of anecdotes and historical developments, and all told in a nutshell, and what happened in the universe over 14 billion years or so. So he narrated the whole thing in about 60 minutes in a very effective way. So thank you very much for a very lucid talk. So as a token of our gratitude and thanks, we would like to offer a memento to Dr. Mark Birkinshaw.